Hi there everyone, welcome to another Chem Complete episode, and for today we are going to be working on the lesson for standard reduction potentials. So this is going to relate back to the previous lecture where we were talking about galvanic or voltaic cells, and these types of battery cells we learned how to basically set them up, create a salt bridge, and we could pass electrons through a voltage meter or some other device in order to generate an electrical current. And we could summarize the value of the voltage as Ecell, and it was equal to the E of the cathode minus the E of the anode. Okay, so for example, when we were working with this, we had an Ecell of 1.1 volts for the cell that we set up that was zinc and copper, if I'm not mistaken, back in that example. Okay, so the Ecell can be standardized, and you can see that up in the title here. So similar to when we're working with thermodynamic properties or equilibrium constants, you can have standardized values that can be tabulated and put into a table when you are at a specific set of conditions. So the set of conditions that you're going to need to standardize when you're doing Ecell calculations are that you want 1 atmosphere, you want to be at 25 degrees Celsius, and any of your solutions, this is the biggest one, should be at 1 molarity. So for instance, in the previous example, in the last lesson, when we were talking about the zinc sulfate would need to be in a 1 molarity solution, or in other words, the zinc 2+ ions would need to be 1 molarity in their solution. And that tends to be where we deviate the most. So if we're going to break away from standard conditions, it's usually due to a shift in molarity, though not always. And there is a way for tackling that. So we're not going to talk about that here. That'll be in another lesson or two where we talk about the Nernst equation. But right now we're going to assume that everything is standardized, and we will see this little knot right up here, the little 0, that's called a knot. So E naught cell is basically just the Ecell standardized for the given reaction, which means we're under these conditions here. Okay. Now, part of standardization is that you have to have some sort of a 0 point or an absolute 0. So for instance, in thermodynamics, we have 0 Kelvin, and we can start basing entropy off of that point for a perfect crystalline structure. So here, we have to arbitrarily set a half reaction to 0 in order to start predicting other half reactions. Because when we create a galvanic cell, and we're passing electrons through the voltage meter, we cannot find the individual values for the cathode and the anode. We simply can take a reading of everything going on that's passing through the voltage meter. So in order to get these half reactions, because they do have some level of potential associated with them, we go with the standardization process, and then we can base it off of that. All right, so it turns out that hydrogen is what the community has accepted as the 0 point. So 2H plus in a 1 molarity solution plus 2 electrons going to H2. All right, now H2 is normally a gas. So if you remember, when we have these cells, they have electrodes or metal plates that we're working with. We don't usually work with gases. And so because of that, they typically will plate the hydrogen onto platinum, which turns out to be a good electrode to use when we're doing this type of reaction. All right, so the E cell for the H plus H2 is equal to 0 volts. And when we put that at 0 volts, if we're looking at any other half cell with the hydrogen half cell, then we could obviously get the full Ecell, and if one of them is 0, then we know that the half cell is the other portion of that. Okay, we'll take a look at that in a second. So this hydrogen process, this is known as a standard hydrogen electrode, an SHE or a SHE electrode. And when we go through this process, this is how we standardize all the other half potentials that we put into these types of tables. All right, so for instance, if I turn around and I set up a galvanic cell and I say solid zinc and zinc 2+, okay, double for the salt bridge, remember the notation, and then H+, and I should put here, sorry, because we are technically standardized, so it's 1 molarity, right? Boundary H2, boundary platinum, right? We need a second boundary here because H2 is a gas and platinum is a metal. So when we're doing that, we put up another one of those single line boundaries when we're creating the written form of the voltaic cell here. And keep in mind, voltaic and galvanic are used interchangeably. So if you hear me saying one or the other, the one that's different than both of those is the electrolytic cell, and we'll talk about that in a couple of lessons. That's not yet. So what we can say here is that the standardized Ecell, okay, is going to be equal to the E cathode and the E anode. Now, in this case, the hydrogen is going to be acting as the cathode, and the zinc is acting as the anode. So the cathode is 0 because it is a standard hydrogen electrode. And when we take from that, we're going to have to find in our table what E for the zinc 2+ zinc process is. Now, we did that in the previous lesson. So if you remember, when we did that, that was a 0.76. Okay, so it's actually a negative 0.76, the value that we're going to have. So E of the zinc 2+ zinc is equal to negative 0.76 volts. All right, and then because of that, right, if we can figure that out, we can then figure out for copper. So if you take a look at this, this is again relating back to the last video, if you remember what we had. So what I can do at this point is I can then say Ecell standardize, right, for the copper 2+ and copper minus the zinc 2+ and zinc. So if I wanted to solve this, it's 1.1 volts equals the E for the copper relationship minus a minus, because this is a minus here and then this value is negative itself. Okay, so it's a minus 0.76 volts. So we make that a plus, and if that's a plus, that means it becomes a minus when I get rid of it on this side, so it would be 0.76 volts. I have to get rid of 0.76 volts here. Okay, and then that means that the E Cu 2+ Cu is equal to 0.34. And these are the values that you find tabulated in your standardized tables. All right. Okay, so I just wanted to bring this up here for a second. So if you take a look, the copper that we just calculated, right, which was for copper 2+ to copper itself, solid copper. And here's the value. It is 0.34, plus 0.34, right? So you can see that we can actually go in and calculate these values by using a standard hydrogen electrode. And as soon as I start finding the half cell potentials for certain metals or certain reactions, then I can pair them up with others and very easily find the half cells for those other counterparts, because I can always get the Ecell running it through a voltage meter for the overall reaction. Okay, so you can see on these charts here. Now, These charts are organized different when you approach them from different books. So some books will list from the most positive values to the most negative values. Some of them do it alphabetically like this. So this one you'll see there's some negative and then some positive and then some negative, because it's going through alphabetically as far as the abbreviations for the various elements. Okay, what you want to realize here is that a more positive half potential value, so when you start getting these positive values like copper was plus 0.34, okay, the larger the positive value for a half potential, the better suited it is at being reduced. That means it's a better oxidizing agent, because oxidizing agents are reduced. So, in a case where we have copper and zinc, if you remember, the zinc was negative 0.76 and the copper was positive 0.34. So a positive 0.34 is larger than a negative 0.76. That means copper should be reduced, and it should be the oxidizing agent found at the cathode. And the zinc should be the oxidized compound. It's the reducing agent that is found at the anode. Okay, so remember, cathode is reduction and anode is oxidation as far as what's actually happening at each half cell and what we refer to it as. Okay, so let's go back and try one additional calculation here. So for this one, let's take two different values, and we are going to bring the table up here in a second. So if you are following along at home, make sure that you have access to a electrochemical table here with your half cell potentials. All right, so here's one of the two reactions. We have silver ion going to silver solid. Okay, and then we have the magnesium 2+, plus 2 electrons going to magnesium solid. All right, so here is the task. Right here, you're given these two different reactions. We would like to set up a galvanic cell that is successful with these two various reagents. So you can have a silver electrode and a magnesium electrode with these types of aqueous ions in solution. So your goal is going to be to, number one, find the half Ecell values by going into your table for each of these, right? So in other words, what is going to be the Ecell for the Ag plus Ag relationship? And then what is going to be the Ecell for the magnesium 2+ magnesium relationship? So when you find those, put those in, and that should only take a second. And then you need to, from those values, predict which would be a better suited anode and cathode, or which one should be reduced and which one should be oxidized. Remember, the one that's more positive should be reduced. So pause the video, try this with a table that you have, or you can go to an OpenStax book like the one that I'm using. It's a free resource on the web, and attempt to solve this problem. We want to find the overall Ecell. Okay, so if you get the half cells and you figure out which is which, try to determine the Ecell. And pause the video and then unpause it when you're ready. Alright, so hopefully you had a successful attempt at this. If you go and you look in your charts, you should have found 0.80 volts, and that's a positive 0.80 volts for the silver, and the magnesium was a negative 2.37 volts. Now, based on this, it should be very obvious the more positive value is the silver, so this would be a good source for being reduced at the cathode. And this leaves magnesium to be what is being oxidized, and that would be associated with the anode. Okay, so remember that Ecell is going to equal the E standardized cathode value minus the E standardized anode value. So we have those at this point. So we can solve for Ecell by saying Ecell is going to equal 0.80 volts minus a minus 2.37 volts. And we end up with, adding that together, 3.17 volts. And that's a positive. Okay, so in order for a galvanic or voltaic cell to be successful, you have to have a positive Ecell when you're working with it. And when I say successful, I mean to actually generate electricity spontaneously through the redox reaction. So you can drive the non-spontaneous versions, but those are done through actually pumping power into a sort of reverse redox process, and that is what electrolytic cells are utilized for. So this is going to bring everything to a conclusion here as far as the half cell potentials and the standard reduction potential tables and how we obtain those values and utilize them. So they're certainly going to come in use as we continue forward with this, because we're going to be calculating Ecell multiple times in some of the future lectures coming up. So hopefully this was helpful for everybody. As usual, if you comment, I will try to get back to you as soon as possible and engage with you on the channel. Leave a like and a thumbs up if this was useful for you, because it does help boost us in the algorithm, and we can make more free content and help you out as you progress through your chemistry career and you are working towards whatever career goals you might have. And then finally, if you subscribe, especially if you hit the little bell, it'll tell you every time that we have a new video coming out, so that you can stay up to date with your studies and all these types of series that we put out. Head on over to chemcomplete.com. We have a lot of free resources there. We also have guides that are available for you to pick up. And if you're struggling, you can pick up one-on-one mentorship and tutoring with me for a very affordable price. So head on over to ChemComplete. You can just browse around. And as always, just watching our videos on YouTube is tremendous support for the channel. So thank you everybody for your attention, and I will see everyone in the next lecture.